This video is to review the lever problems that you were assigned to work on. The first problem states that we have a first-class lever. It also states we are in static equilibrium. It gives us three different values. It gives us our FR, right, which is the 50 pounds. It gives us our FE, which is the 15 pounds. And it also says the lever's effort force is located 4 feet from the fulcrum. Okay, 4 feet from the fulcrum. So let's sketch a first-class lever. First-class lever is where the FE is located on one side and the FR is located on the other side. So there's our sketch. Now it asks us for the ideal mechanical advantage of the system. Now the ideal mechanical advantage of the system is also called AMA. Okay, so our AMA is going to equal to FR over FE. Now we just said that we know our FR and our FE, so all we have to do is plug in the values. And if we do the math, we come up with 3.33 for our AMA. The next question also says we are in static equilibrium. Calculate the length from the fulcrum to the resistance force. Now using our equilibrium equation, which is FE times DE equal to FR times DR, and it says calculate the length from the fulcrum to the resistance force. Fulcrum to the resistance force, which is our DR, okay? From the fulcrum to the effort force is the DE. So we need to rearrange this equation to solve for DR, right? So DR would equal to FE times DE, all divided by FR, right? Now we know our FE, which is 15 pounds. We know our DE, it says 4 feet. We know our FR, which is 50 pounds. And if we do the math, we come up with a DR is equal to 1.2 feet. Okay, so there's the first problem. The second problem says that we are working with the wheelbarrow. And if you remember, we were talking about examples of different kinds of levers. The wheelbarrow represents a second-class lever. So the first thing we want to do is draw a second-class lever. A second-class lever would be represented with the fulcrum at the end and the effort force pushing up on the other side, and the resistance force would be in the middle, okay? So it tells you you have a 200-pound load, right? So that load is going to be your FR, 200 pounds. It also says the length from the wheel, so the wheel is going to be the fulcrum. The length from the wheel to the center of the load is going to be your DR, and it tells you your DR is 2 feet. It tells you the length from the wheel and axle to the effort force is 5 feet. So from the fulcrum to the effort force, which we also call DE, is 5 feet. So DE is equal to 5 feet, okay? So we've sketched the lever and we've written out what it is that we know. Now the first thing it asks you for is to calculate the ideal mechanical advantage. The formula for ideal mechanical advantage is going to be DE over DR. And we just said we knew what our DE was, which was 5 feet. We knew what our DR is, which is 2 feet. So that would give us an IMA equals to 2.5. Next, it tells us we are using static equilibrium equations. Calculate the effort force, which is our FE, needed to overcome the resistance force in the system. So we can use our equilibrium equation. And we're solving for FE, right? So we need to rearrange this to solve for FE. Okay, we know what our FR is, right? 200 pounds. We know what our dr is, 2 feet. We know what our dE is, 5, right? So if we do the math, we come up with an Fe equals to 80 pounds. All right, the last problem is about a pair of 4-inch long tweezers. 4-inch long tweezers. Okay. And the tweezers are used to remove a wood splinter from a patient. Okay, so let's draw a pair of tweezers here. Okay. The technician is applying a 1 pound of squeezing force to the tweezers. Now when we squeeze on a pair of tweezers, we're usually squeezing here in the middle somewhere. Okay, so it says applying 1 pound force. So that means our Fe is going to be 1 pound. Okay, now the tweezers here, right here is where the fulcrum would be, is essentially 2 third-class levers, but we're really just interested in one of the levers. So we know what the Fe is. Now it says if more than 1/5 pound of force is applied to the splinter, so if we assume that the splinter is here at the end, then the Fr is going in the opposite direction of the Fe. So our Fr is going to be 1/5 of a pound. It will break and become more difficult to remove. So the other thing we know is that the tweezers are 4 inches long, right? So from here to here, all the way to the end, we know is 4 inches. And that's also the distance from the fulcrum to the resistance force, which would also be our dr. So dr is equal to 4 inches, okay? So it asks us, what is the actual mechanical advantage of the system? So the AMA is going to be Fr over Fe. Now we already know what our Fr is, right? So 1/5 of a pound divided by our Fe, which is 1. So our AMA is going to equal to 1/5. Now it says, the next problem says, using static equilibrium equation, so we're going to use our equilibrium equation, which is Fe times dE is equal to Fr times dr. Calculate how far from the fulcrum the tweezers must be held in order to avoid damaging the splinter. So how far they must be held, so that would be this distance here. And that distance is being measured from the fulcrum to the effort force, which would also be our dE. Okay, dE. Oops. dE. So we need to rearrange the equation to solve for dE. So Fr dr divided by Fe. Okay, and we know all these values. We know what our Fr is. We said that our Fr is 1/5. We know that our dr is 4, and we know that our Fe is 1. So all we have to do is multiply the 1/5 times the 4, and that gives us 1/5 times 4 gives us 4/5 of an inch. Or 0.8 inches. Okay. Okay, so that concludes the problems for the levers.